तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we shall continue our discussion on BiCMOS logic circuits and keep comparing the performance with respect to CMOS and see how it actually is an improvement on CMOS in quite a number of applications. So, before we do that, let us see how in a CMOS environment, okay, one would drive a large capacitive load. Okay, because we have already seen that BiCMOS would be an advantage if we are driving a large capacitive load, because the delay does not increase at the same rate as it does in the case of a CMOS. So, first, if you want to really actually make a comparison, we have to see how you use a CMOS to drive a capacitive load. So, this is a CMOS inverter. Okay. Now, suppose before we go into that, let us take up a small example. You have a CMOS inverter driving a similar CMOS inverter. Okay, that is, you have an inverter. Right. Yeah. Now, if suppose the delay, okay, of this first inverter, okay, is given by tau. Okay. Okay. Now, suppose we increase the widths of all the transistors in this circuit. Okay, that is, there are 4 transistors by a factor alpha, say. Okay, that is, we make this whatever is the width of these transistors, we increase them, all the 4 transistors. What is going to be the new delay? Is tau going to be changed, or is it going to remain the same? That is the question. Now, you see that what happens to the capacitance as seen by the first inverter? The capacitance goes up by a factor alpha. Okay, and you know that the delay, okay, this tau is proportional to, we have seen in all the expressions that it is dependent on the load capacitance by the transconductance parameter. Okay. Now, this CL is proportional to W into L ratios. Okay. So, this one will be again proportional to W into L, okay, and K is proportional to W by L. Okay. So, you see that what is going to happen is, if you increase the widths of all the transistors, well, CL refers to the input capacitance of this inverter, that is going to go up because W has gone up. Okay. And the K factor, or the transconductance parameter of the driving transistor, okay, that also goes up by the same factor, with the result that the delay remains unchanged. Okay. That is, again, if you increase the widths of all the transistors by the same amount, okay, the delay, okay, does not change, because the capacitance is going up as well as the driving capacity is going up. The current charging the capacitance is also going up by the same amount. Okay. But if you take the lengths of the devices, okay, suppose you increase the lengths, all the lengths of the transistors by a factor alpha, say, what is going to happen? The capacitance goes up by a factor alpha, the current goes down by a factor alpha, okay, because the current charging the capacitance is proportional to W by L. So, the delay goes up by a factor alpha squared. Okay. So, okay. So, now if you look at it from another angle, if you reduce the lengths by a factor alpha, in fact, the speed is going to go up by a factor alpha squared, because the delay is going to go down. Okay. by a factor alpha squared. So, that is the driving force behind reducing the dimensions. So, the lengths of the transistors must be made as small as possible, okay, from the delay point of view. Okay. Now, all right. So, again this is the tau is the delay for this inverter if it is driving a similar inverter. Okay. Let us call that delay equal to tau. Okay. Now, suppose this same inverter, okay, this same inverter is driving a capacitive load CL, say, okay, and suppose the CL, okay, is equal to Y times the Cin of this same inverter, that is the input capacitance of the same inverter. Okay. What is going to be the delay? What has happened is the capacitance has gone up by a factor Y. Okay. So, if the delay is tau for driving a capacitance equal to Cin, okay, if you are driving a capacitance CL, obviously the delay is going to be Y times tau, okay, because the delay is proportional to CL by K. K remains the same, you are the same inverter driving a load. Okay. So, in this case the delay is going to be Y times tau. Okay. All right. Now, suppose so this is a scheme, you have a CMOS inverter driving a capacitive load. Now, let us take another see how we can in fact reduce this delay. Okay. Now, suppose here itself, instead of having this inverter driving the load directly, we have this particular scheme, that is you have inverters, a series of inverters, a cascade of inverters, okay, all right, like this, one inverter like this, then I think I should basically, okay, you have an inverter like this, then you have a large number of inverters one after the other, okay, driving this load CL. Okay. So, this is our original inverter, okay, and we make it this way, that suppose the original inverter is like this, that is the PMOS and this is the NMOS. Okay. All right. The PMOS, you have the length of the PMOS LP and the width is WP. Okay. And the NMOS here, the length is Ln and the width is Wn. Okay. Then the next inverter, what we do is we retain the same length, okay, but we make this width alpha Wp and we make this width alpha Wn. Okay, that is increased by a factor alpha. So, what is the delay of this inverter driving this next inverter? That is alpha times tau, okay, because this width, the width of the driving of the transistor it is driving, the transistors in the inverter it is driving is increased by a factor alpha. We have already seen that. So, this is alpha tau. The next inverter is say alpha squared Wp and alpha squared Wn. Okay. Now, what is the delay of this inverter, the second inverter driving the third inverter? Okay. Here what has happened is the widths of the transistors in the third inverter is alpha times the width of the transistors in the second inverter. Okay. So, again the delay is going to be alpha times tau. Okay. If this had also been alpha times Wn and alpha times Wb, the delay would have been tau itself. Okay. We have seen that if you have equal widths, okay, it is the same tau. All right. So, this is, so if you have n such stages, okay, so that, all right, alpha times you have n such stages and alpha to the power n is equal to y, where y is what? Y is CL by Cin. Okay. So, this is alpha times the capacitance of this input capacitance. This is the input capacitance of the second stage is alpha times this. Okay. The third one is alpha squared times Cin. Okay. And the final CL is going to be alpha times alpha to the power n times Cin. Okay. That is the capacitance. So, you have alpha to the power n, if you have n stages, okay, you have alpha to the power n is equal to y, okay, where y is the ratio of CL to Cin. Okay. All right. Now, so what is the total delay in this case? You have n stages and each stage has a delay of alpha times tau. So, the total delay is n times alpha tau. Okay. So, in this scheme, total delay is equal to n times alpha tau. Okay. So, you see that in this, if you have a cascade of inverters like this, the total delay is n times alpha tau, whereas if you were driving it directly, okay, it would have been y times tau. All right. Now, let us see. Okay. Basically, so we will call this the cascade. Okay. Total delay, we will call it a tau cascade. Okay, a cascade of inverters, and tau direct. Okay. So, y tau is the delay of the direct when it is directly driven. So, tau cascade by tau direct is equal to n times alpha tau divided by y times tau. Okay. So, this and what is n actually? N we know is alpha to the power n is equal to y. Okay. So, we know that alpha to the power n is equal to y. So, we can write n ln alpha, if you take the ln on both sides, is equal to ln y. Okay. So, n is equal to ln y by ln alpha. Okay. So, here we have tau cascade by tau direct becomes equal to ln y by ln alpha, okay, tau alpha by y. Okay. So, alpha by ln alpha into ln y by y. Okay. So, we call this say x times ln y by y. See, this ln y by y is a constant depending on the capacitance you are driving. Okay. If y is the ratio of the load capacitance to the input capacitance, okay, which is a constant. Now, what you have to do in our design, we have to choose the number of inverters we want to put and the ratio of the widths of the inverters. Okay, that is the design which we have to take up. So, what is going to be the factor alpha? Okay, that is what we have to see. Now, obviously, what our aim should be to reduce this as far as possible. Okay, tau cascade by tau direct should be as small as possible. So, we have to minimize the value of x. Okay, and what is x? Alpha by ln alpha. All right. So, alpha by ln alpha we have to minimize. So, we have to put we have to differentiate this alpha by ln alpha and put it to 0. Okay. Okay. So, if you differentiate this alpha by ln alpha, what do you get? You have ln alpha minus alpha okay, all right, and which means that ln alpha is equal to 1, which means that alpha is equal to E. All right. So, if this is the case, if alpha is equal to E, then what is this tau cascade by tau direct? So, x is equal to, so alpha is equal to E. So, alpha by ln alpha is equal to E. okay, alpha is equal to E, ln alpha is equal to 1. So, that is going to be E. So, basically it becomes E times ln y by y. Okay. So, that is the tau cascade by tau direct. Okay. We can take an example, okay, and see how much it is effective. Say suppose let just we are taking some numbers, let y is equal to, I am just choosing an arbitrary number, this 2981 is taken because that is equal to e to the power 8. Okay. All right. So, ln y is going to be equal to 8. Okay. So, tau cascade by tau direct is going to be 8 e by 2981. Okay. And this is 8 e is around 21.75 by 2981. So, what you see is, if you are using a cascade of inverters, okay, you have substantial savings in delay. Okay, this is less than 1% of the delay you would normally have had if you would have been driving the load directly. Okay, all right. If you had been driving the load directly using that CMOS inverter, whatever delay you would have had, by having a cascade of inverters like this, the delay is going to be about even less than 1% of that delay. Okay. So, usually in a CMOS environment, okay, when you are driving large loads, okay, you have to use a cascade of inverters like this. Especially this type of circuit is important. For example, in a clock circuit, in a clock generator circuit, you know that in a large circuit, okay, you will have a master clock somewhere, okay, and that clock output may be going to a large different regions in the circuit. Okay, it is maybe driving different parts of the circuit. Okay, and so the effective load for that clock generator is going to be enormous. Okay, so you will have to have such drivers for that. Okay, because it is important, because if the delay is too much, basically you have to use a slower clock. Okay, all right, you cannot go for very high frequency clock. Okay, so in order to reduce the delays, okay, you have to go for buffering. Okay, or you use a cascade of inverters like this, all right, with gradually increasing dimensions. All right, the inverters will have gradually increasing dimensions. So, in this particular case, you will have 8 such inverters, okay, followed by the load. Okay, and because you have to reduce the delays. Okay, so on the one hand, okay, you are reducing delay, but of course you are paying for it in terms of area. Okay, that is, you require so many inverters. Not only that, the sizes of the inverters are gradually increasing, so that the last inverter will be a very big inverter. Okay, the width of the transistor is going to be very large because it is increasing in a geometric fashion. Okay, all right. So, what we shall now do is, we shall see how the BiCMOS, okay, can be effective in actually driving such large loads, okay, by saving area, okay, when compared to the CMOS counterpart. Okay, we shall take a small we shall take an example for that, okay, and try to understand with that. Now, suppose you have an inverter, a CMOS inverter with the different dimensions are WP is 10 micron, WN is 7 micron, and of course LP is 1.5 micron, and Ln is 1.5 micron also. This, of course, as you see that the lengths of the devices are always kept at the minimum value. Okay, it is, we only play around with the widths. Okay, because the as we have seen, the delays, okay, are mostly determined by the lengths. Okay, all right. So, and for this inverter, okay, suppose it has to drive a load capacitance of 2 picofarads, okay, and also let us say that in this CMOS technology, the oxide thickness, okay, is given as 225 angstroms. So, that is the specified, okay, 225 angstrom is the oxide thickness, okay. These are the dimensions of the devices. This is the load capacitance which it has to drive. Now, let us we shall see in our design how many stages of CMOS we require, okay, for driving this load, and what are the sizes or the dimensions of the different transistors. Okay. Now, so first what we have to calculate is the CL to C in ratio, okay, that is the input capacitance of this particular inverter. Okay. So, we have to take the total area. So, what is the total input area? That is WP into LP plus WN into LN. Okay. So, area is equal to WP into LP plus WN into LN, okay, is equal to, so 10 into 1.5 is 15 and 7 into 1.5 is 10.5. So, it is 25.5 micron squared. Okay. So, C in is equal to epsilon A by T ox. What is epsilon? For silicon dioxide it is 3.9, okay, into 8.85 into 10 to the power minus 14, okay, that is epsilon naught, this is epsilon r, okay, into area 25.5 into 10 to the power minus 8 per centimeter. This is in centimeters, all in CGS units, okay. This is farad per centimeter, this is centimeter squared, okay, by oxide thickness, okay, 225 angstroms, okay, 225 into the power minus 8. Okay. So, this comes to 39, I just give the result, 39.3 femtofarad. Okay. So, if this is 39.3 femtofarad, so the load capacitance is given as 2 picofarad. Okay. So, CL by C in is equal to 2000 by 39.3. This comes to almost 51. Okay, which also happens to be almost equal to e to the power 4. Okay, all right. So, what is going to be the dimensions of the individual transistors? Okay. So, the first one is, okay, this is WP, this is WN, all right. So, this is all 1.5, the lengths do not change, this is all in microns. WP is 10, okay, slightly wider than WN in this case, okay, 7 here WN, all right. The next device is going to be E times. All this what we have done is we have taken that the widths of the transistors is going to be E times, increasing by a factor E, okay, all right. So, this is going to be wider, okay. So, this is going to be 27.18, okay, and this is going to be 19, okay. Then the third okay, this is going to be 70, almost 73.9, okay, and this is going to be 52. Okay. Then the next one is 200, and this is going to be around 140. Okay. For all the transistors, the lengths remain same as 1.5 micron. So these are the 4 stages. So from here to here, it is going to be E, okay, E squared, E cube, and the load is again another E, that is e to the power 4. Okay. So CL by Cn is equal to e to the power 4. So you have these 4 stages driving the capacitance. All right. So just I am quoting from a report from which I took this example. Okay. They were driving the same load and using CMOS. Okay. They had to fabricate this, they required an area of 16,600 micron squared, and the delay was 1.9 nanoseconds. Okay. They fabricated the same thing using a single BiCMOS inverter, okay, where the MOS dimensions were the same as this first inverter, and they just included a bipolar transistor, just as we had discussed last class, that you have the CMOS, okay, with a bipolar transistor, BiCMOS inverter, normal BiCMOS inverter, where the MOS dimensions are given by the smallest device here. Okay. So this is for CMOS. For a BiCMOS, the area required was just 2,500 micron squared, and the delay was 1.4 nanoseconds. Okay. See the gain, see you are driving a load which is 51 times the input capacitance. Now if the bipolar transistor is able to give you a current gain of more than 50, okay, the same CMOS inverter, okay, when you compare with the same CMOS inverter driving the same load, okay, you are going to get a lower delay, isn't it? So you see that this in fact gives you a lower delay compared to the CMOS inverter. Okay. Not only that, the area requirement is much smaller because you are using just the smallest size devices here. Okay, and you just have extra some bipolar transistors, whereas here you use progressively larger devices, okay, and which requires a lot of area. So using BiCMOS drivers to drive large capacitance loads, you not only gain in terms of speed, but also you require a much smaller area. Okay. So that is the advantage of BiCMOS drivers over CMOS drivers, and it is now being widely used, okay, wherever you want to drive. For example, in memories, for example, we shall see that also after address decoder, okay, you have the memory cells to be driven. Okay. So so if you have a 1 megabit memory, okay, you will have 10 to the power 6 cells, okay, which may be 1000 by 1000 array. So the output of an address decoder must drive 1000 gates, okay, which means a large capacitive load. Okay, and BiCMOS driver is obviously going to be much superior compared to the CMOS driver. Okay. So there are many applications, okay, where you require large capacitive loads to be driven, and obviously the BiCMOS inverter or BiCMOS driver is going to be superior in that respect. Okay. All right. So that is the example of a BiCMOS driver. We shall take up some more examples, okay, where BiCMOS is used. Here what we have taken is the conventional BiCMOS inverter as a driver. Okay. So instead of the CMOS inverter, you use a BiCMOS inverter, okay, or you may use, instead of the CMOS gate, for example, a NAND gate, you may use a BiCMOS NAND gate, okay, where the output you have a transistor which with the help of the current gain it gives you lower delays. Okay. But in many other applications, okay, it is the judicious use you do not use the BiCMOS as such as gates, okay, but by the judicious use of bipolar transistors, okay, you can increase the speed of the operation. Okay. We shall take up one more such case, okay, in the case of an adder circuit, all right, and we shall see how incorporating a bipolar transistor in an essentially CMOS environment, okay, you get higher speed. Okay. So, the next example we shall take up is an adder circuit. So, I shall just give you a brief introduction about adder, just maybe as to remind you, okay, the carry lookahead adder. I think you are aware of it, but anyway, just to give you an idea what is a carry lookahead adder. Okay. Normally, if you have two types of adders, one is called the ripple carry adder, where if you are say for doing a 4-bit addition, okay, you have 4 adders, okay, and what you do is you have the inputs to each stage, okay, and it is the the output of each adder is going to be the sum and carry outputs, okay, and what is going to happen, you have the sum output say coming out, and the carry output is going to come in as go to the next stage, okay. So, it is just rippling through all the stages, okay. So, if you have a 32-bit adder, you know, then the output of this has to go here, then the next will change because of that, and so it is a rippling effect, okay, and it takes a long time, okay. What a carry lookahead adder does is it prepares this carry inputs to each stage beforehand, okay, in a very short time, so that even for the last bit, okay, the addition does not take much time, okay. So, we shall just see what a carry lookahead adder is, and then we shall see how incorporation of bipolar transistors in a CMOS environment actually can speed up the operation, okay. So, basically a full adder, okay, which has got 3 inputs, you know, that is the 2 inputs to be added and a carry input from the which comes from the previous stage. So, a full adder can be constructed using 2 half adders, okay. All right, what is a half adder? A half adder has got 2 inputs, okay, and 2 outputs. One is the sum output and the other is the carry output, okay. So, if you know that if the inputs are 0 0, sum is 0, carry is 0. If one input is 1, the other is 0, sum is 1, carry is 0. If both inputs are 1, sum is going to be 0, carry is going to be 1. So, basically the sum output which you have is the exclusive OR function of A and B, if you consider them as the inputs as A and B, okay, and the carry output is equal to AND function of A and B, okay. Now, let me call this exclusive OR of A and B, we call it the P term, okay, A exclusive OR B. Why we call it P, I'll just come to that, and this is called G, okay, A B. So, P stands for propagate and G stands for generate, okay. So, you have the propagate term and G is the generate term, okay. Now, you feed this directly to the next adder, okay. The carry in which you have to this stage, all right, goes in as the other input to this half adder, okay, all right. So, here at the output you have sum is equal to exclusive OR. So, this half adder again. So, the sum output here is going to be the exclusive OR of the 2 inputs here. So, this is exclusive OR of A, exclusive OR of B, exclusive OR of the carry input, okay. And here what you feed is so here again this is going to be the AND function of the two inputs. All right. So, here you have one of the input is P and the other input is C in, P C in, okay, and you take an OR of these two carry outputs. All right. So, the carry output is actually equal to G plus P into C in, okay, where G is equal to AND of A and B, okay, and P is equal to exclusive OR of A and B. Okay. Now, G is called generate because it generates a carry if, well, it is going to be high if both A and B is going to be high. Okay. So, it generates a carry. If A and B are both high, that is the inputs to the present both inputs are high, of course, you are going to have a carry irrespective of carry in or whatever, all right, you are going to have a carry out. So, it generates a carry, all right. So, you will going to have a carry out if G is high. Okay. The other case where you can have a carry is that you had a carry from the previous bit, that is there was a carry input, okay, and you are propagating that carry. Okay. That is there was a carry input from the previous bit, okay, and now if one of the inputs, other inputs A or B is high, okay, then you basically propagate that carry to the next bit. Okay. So, P is going to be high, it is an exclusive OR function. So, if any A or B is high, any of them is high, okay, the output is going to be the P is going to be high. Okay. All right. So, if C in is high and either of A and B is high, you have the carry output. So, basically the carry input is propagated to the output. Okay. So, P is going to be high if A exclusive OR B is high. Okay. So, you have a carry output if either you generate a carry in this present bit or you propagate whatever carry in is just propagated to the output. If P is high, okay, and C in is high, then also you are going to have a carry output. So, this is for a particular bit, okay, you have the carry output. All right. Now, if you consider say a 4-bit adder, okay, what you can do is you can think of it this way. So, the input you have C0 is the carry input to the 4-bit adder, okay. C1 is equal to, so you have the inputs. So, for the first bit, okay, you have A0 and B0 at the inputs, okay, and basically you have which gives rise to G0 and P0. Okay. So, basically if you have this all these zeros here, okay, you will have P0 and you will have G0, okay, everything is zeros. If it is for bit 1, okay, this one will be A1 and B1, you have G1 and P1. Okay, where G1 is A1 and function of A1 and B1 and P1 is exclusive OR of A1 and B1. Okay. So, what is C1? C1 is G0 plus P0 C in, okay, that is actually the C in, okay, or okay, I think we should pull it C0, which is actually C in, all right. Okay, this is C1 which goes as the input to the first bit. Okay. C1 is G0 plus P0 C0. Okay. So, for first bit you have the inputs A1, B1 and C1, okay, bit 1, okay, this is for bit 0. So, for the next C2 will be equal to G1 plus P1 C1. Okay. And what is C1? C1 is G0 plus P0 C0. Okay. So, we can write G1 plus P1 into G0 plus P0 C0, okay, which means this is equal to G1 plus P1 G0 plus P1 P naught C0. Okay. all right. So, you can see the logic here that C2, that is the carry, there is going to be a carry output or the carry input to the bit 2 if there is a carry generated at bit 1 or there was a carry generated at bit 0 which got propagated through P1 or there was an input carry which got propagated through both P0 and P1, all right. So, that is how you get C2. Similarly, you will get C3, okay. You can do it the same way, it will be G2 plus P2 C2 and then you instead of C2 you write the same thing, okay. So, what will you get? You will get G2 plus P2 G1 plus P2 P1 G0 plus P2 P1 P0 C0, okay. Similarly, C4 you will get as G3, I am just writing it down, okay, plus P3 G2 plus P3 P2 G1 plus P3 P2 P1 G0 P3 P2 P1 P0 C0, all right. So, these are the terms. So, the interesting thing here is that what you can do, you already know these things, okay. So, you can instead of C4 you see if it was a ripple carry you have to go through all the stages before you do it, but here you can generate these things. So, basically the scheme which you are going to have now is you are going to have, suppose what we do is, suppose we have a 32-bit adder, okay. What is done is, see if you have a 32-bit adder, this is going to become a very cumbersome expression to do it, okay. So, you break it up into say 8 4-bit adders, carry look ahead adders. So, you have one 4-bit carry look ahead adder, okay. So, here you have the inputs say A0 to A4 and sorry A0 to A3 and B0 to B3, okay, and you have the outputs S0 to 3. So, C0 comes in here, okay, and C4 goes out, okay, and then this is another carry look ahead adder, okay, where you have the inputs A4 to A7, B4 to B7, okay, and you have the outputs S4 to 7 and C8 goes out. So, basically this is the 4-bit carry look ahead adder, all right, and then you are going to have 8 such carry look ahead adders, all right. And so, what is the critical path in this circuit? The critical path is this transmission of this carry look ahead carry, okay. It has to go from C0, so to the 8th adder or the 8th 4-bit carry look ahead adder. So, only when this is available, made available to that carry look ahead adder, okay, can that output be a valid one, okay. So, this is the critical path for this carry look ahead adder, and this must be properly designed because the total delay of the 4-bit carry look ahead adder is going to depend on this path, okay, how fast this is, okay. So, basically if you look at it this way, the 4-bit carry look ahead adder, okay, will consist of, I just draw it like this, you have 4 half adders, okay. So, you have A naught, B naught fed here, A1, B1 fed here, A2, B2 fed here, A3 and B3 fed here. Okay. And what is coming out of this half adders? You have the P's and G's, all right. You have here you have P naught and G naught, here you are going to have P1 and G1, P2 and G2 and P3 and G3. Okay. So, all this is going as input, okay, to what is called a carry propagation circuit. So, this is the carry propagation circuit, okay, which has as its input C naught, okay, and passes out C4, which is going to be used by the next 4-bit carry look ahead adder. Okay. And then, and this as we have seen that in order to evaluate C4, what you require as inputs, if you look at this expression here, what you require as inputs is C naught, okay, as well as all the G's and P's. So, if this is available, you can generate C4. Okay. So, that is what it requires at the input. Then you have another circuit, okay, which is called the carry generation circuit. Okay. So, which basically generates the carries for the different bits in this 4-bit carry look ahead adder. So, you are going to generate the carry that is C1, C2, C3, all right. So, as well as of course, you require C naught also. So, what you do is so this requires as inputs, what does it require as input? It requires input as C naught is required, okay, again C naught is required, and the different P's and G's, okay, up to that stage. So, again you have the different P's and G's coming to this circuit also, all right, and you have C naught also coming here, okay, and what you get out of this circuit is you will have the different carries C naught, C1, C2 and C3, okay, and this then you have another half adder, another bank of 4 half adders, okay. This is another set of 4 half adders which you have, okay, one another, okay, and these half adders, okay, require as input the P's and the C's. Okay, we have seen the model for a full adder, okay, where sum is equal to exclusive OR of P and C, okay, P, where P is again the exclusive OR of A and B, that is already available. So, this is going to give you S naught, okay, again for this half adder you have the inputs P1 and C1 is required. So, S is equal to exclusive OR of P1 and C1, basically you just require the exclusive OR here, okay, because the carry in is here, okay. So, you have S naught, S1, S2, so this again the P's are extended up to this, okay. So, you have S1, S2, S3. So, this is a 4-bit carry look ahead adder where you have the input C naught, okay, you are getting the and all the inputs, the input bits A naught to A3 and B naught to B3, and what you are getting at the output is S naught, S1, S2, S3, okay, and the output carry C4, okay. Now, as we said, now this in this part of the circuit, what the crucial part of the circuit which is gives rise to the delay is the carry propagation circuit, because what it is doing is it is taking the carry in and it is passing out the carry, okay. Here the carry generation circuit is actually a subset of this particular circuit, you can say, all right, because if you look at the expressions, C1, C2, C3, it is a simpler expression compared to C4, and you are just using the same things, all the P's and G's and the C naughts, Okay. So, in this part of the circuit you have 2 half adders, okay, and then you have the 2 carry propagation circuit and the carry generation circuit. The delays in the carry generation circuit, that is C0 is already there, C1, C2, C3, okay, that is going to obviously take less time than C4, okay, all right. And C4 is very crucial because as we have seen that in a 32-bit adder you are going to have 8 such 4-bit carry lookahead adders, and the delay, the C4 has to go in as the next 4-bit adder and as the input of the carry propagation circuit of the next 4-bit adder, and you will generate C8 which has to be passed down to the next 4-bit adder to generate C12 and so on. Okay. So, this is the most crucial part in say a 32-bit adder, how fast you can generate this carry propagation circuit. How fast you can generate the carry in this carry propagation circuit. Okay. Well, in a CMOS environment, okay, we shall see now in the next class, we shall see how this is generated in a CMOS environment, okay, and how you can improve the circuit or basically reduce the delay by using bipolar transistors, okay, to create a BiCMOS type carry propagation circuit, okay. And we shall see that by just using very few bipolar transistors, it is not that you are having you are replacing a CMOS NAND gate by a BiCMOS NAND gate or a CMOS inverter by a BiCMOS inverter, but by the judicious introduction of bipolar transistors you can improve the delays, okay, all right. So, it is you have to see where you want to introduce that bipolar transistors and how it can improve the speed, all right. So, we shall take that up in the next class.